Hey everyone, today we'll discover how to integrate rational functions using long division. Let's get right into it. Here we have the indefinite integral of 3x minus 7 divided by x plus 1 dx. So if you remember the idea behind long division with polynomials, we want to divide one polynomial into another polynomial to simplify it as much as possible. There are only some cases, however, where you actually can use long division. The first of which is when the degree of the numerator is equal to the degree of the denominator. So in this case, we see that the degree of the numerator, 3x minus 7, is equal to the degree of x plus 1, our denominator. Thus, we can use long division to simplify this rational function. So if we work out this long division, we end up with x plus 1, and we're going to divide that into 3x minus 7. So we see here that the x goes into 3x 3 times, so that becomes a 3 up there. So we're going to subtract x times 3, which is 3x, and then plus 1 times 3, which is 3. Subtracting that, we get a 0 minus 10, or just negative 10. And so now here, we can't divide negative 10 and x plus 1, so that actually just becomes our remainder. So that's a negative 10. That means that we can write the rational function as 3 minus 10 over x plus 1. So whatever our remainder is, we have to divide by whatever our denominator was. Having computed the long division, we saw that the rational function was just equal to this, and we can rewrite this integral on the left as these two integrals on the right. So the integral of 3x dx is pretty simple, but this one might be a little bit of trouble. But if we use u equals x plus 1 as a substitution, it actually simplifies pretty nicely. So that tells us that du is equal to dx, so we get negative 10 times the integral of du over u, which ultimately just simplifies to negative 10 times ln of the absolute value of u. Now this integral we can compute very easily. That'll just be 3x, and we can substitute in what our u was. So when we do that, we just end up with 3x minus 10 times the natural log of the absolute value of x plus 1 plus c. Ladies and gentlemen, that right there is our final answer. Here we have the integral from 0 to 3 of 2x squared plus 5 divided by x minus 2 dx. The second and final case where we can use long division is when the numerator's degree is greater than the denominator's degree, like it is with this rational function. So let's compute the long division. So we'll have x minus 2 dividing into 2x squared plus 5. And I left a little space here because we don't have a term with just x. But anyway, if we see how many times x goes into 2x squared, we get 2x. So multiplying everything by 2x, we have x times 2x, which is 2x squared, minus 2 times 2x, which is minus 4x. So subtracting everything, we have 0, and then plus 4x, since we have minus negative 4x plus 0. And so now we can drop down this 5 over here, so we have plus 5, and now we analyze how many times x goes into 4x, and that happens to just be 4. So now we multiply everything by 4 when subtracting, so x times 4 is going to be 4x, negative 2 times 4 is going to be negative 8, so when we subtract everything we have 0 and 13, which is positive. And that right there is going to be our remainder, so we have a remainder of 13. And that tells us that we ultimately just divide into 2x plus 4 plus 13 divided by x minus 2. After doing the long division, we saw that the rational function just simplified to this, and this integral here on the left can just be written as these three integrals on the right. So this integral and this integral is pretty easy, but this one I'd say requires a u substitution. So u is equal to x minus 2 tells us that du is equal to dx. And if we plug in everything into the integral, well, we get the integral of du over u. And I won't worry about the bounds right now because I will plug in the value of u in later. So computing the antiderivative, we do end up with the natural log of the absolute value of x minus 2 when we plug things in. And we're going to evaluate that from 0 all the way to 3. And then computing this integral, well, we will get 4x, and we add everything else. This integral becomes x squared added to everything else, and we'll evaluate everything from 0 all the way to 3. So when we plug things in, we just end up with 3 squared plus 4 times 3 plus the natural log of the absolute value of 3 minus 2, and then from that we subtract 0 squared plus 4 times 0 plus the natural log of the absolute value of 0 minus 2. And then simplifying everything, well, we do just end up with a 9 plus 12 plus the natural log of 1 minus 0 plus 0 plus the natural log of 2. And so if we simplify absolutely everything, well, we end up with just a 21 here and a negative ln of 2 there. So our final answer is simply 21 minus the natural log of 2. Now let's say we had a problem like the integral of x plus 1 divided by x squared plus 1 dx. Well, here we cannot use long division because the degree of the denominator is greater than the degree of the numerator. So here in this case, actually, we'd have to split it up into two separate integrals, then take a u substitution, and then we'd find our antiderivative. But if the denominator's degree is greater than the degree of the numerator, we cannot use long division. That just about wraps everything up. Thank you for watching, and have a great day.